Recording is rolling. Today is Thursday, September 8th. We're gonna warm up with some graphs related to projectile motion. You guys remember we've been doing projectiles for last few days. We've got a couple of classic setups, our like cannon on a cliff, something like that. Actually, we're about to make some graphs related to this scenario, right? And you might also come across something like this, where you have something like a cannon on the ground. Those are both projectile paths, right? Something like that. Okay. And I have been wanting to get to a lab with you guys. So you guys see this projectile launcher. I don't know if there's like a yellow ball somewhere around the room. They go like scattering somewhere, but you take a ball, throw it here, but launch it here. I'll show you guys. Oh, anyway, you click this, put this in place, pull the thing, and it'll like launch this ball. So we're going to use this in a lab. Again, I want to get to that. I'll have to push it off next week. It's gonna be how it is. Okay. It's most linear motion quiz. Linear motion quiz was due a few days ago. If you turn it in by now, then I got those graded yesterday, so those are up on Focus. If you haven't turned that in yet, then get them in real soon, because I do want to get this back to you guys, but I have to wait till I get them all first. All the answers we covered in class at some point. So remember, I've been recording all these videos, uploading them to Classroom. So every single quiz question is somewhere that we did in class at some point. Also, you guys know that the first enrollment today, right, we are like 1/8 the way through the entire year. Okay, so teachers have a few days to get their grades in, but yeah, at some point you got to upload grades. So yeah, make sure for all your classes got everything turned in. Okay, and then the homework I'm picking up from you guys by Monday is just this page with these conceptual questions. Remember, on the opposite side has some projectile questions, and what I want you guys to do is just answer all the conceptual questions, which we're about to do on the Kahoot right here in a few minutes, and then just follow along just with these, just whichever ones we do in class. And then of course the main focus of this class is just the conceptual questions, right? So when I get you guys this quiz coming up pretty soon, it's going to be like mostly focused on these conceptual questions. Okay, so here's my plan. I want to get you guys the next take-home quiz tomorrow, so you guys will have the weekend to look at it. Okay, mostly conceptual questions. There we go. Kahoot. Yeah,
I will be here tomorrow.
We'll be here tomorrow. Okay, well, I don't have the quiz printed yet, so I'll have to get to yeah. I'll have to get to you when you come back. Okay, but yeah, so the quiz won't be due Monday. It'll be due something after that. Okay, then I'll pick up this page on Monday, so you have both side by side. You can say, okay, here's my homework. Here's some projectile questions. If there's like anything that looks any bit mathy, right? And then yeah, if you guys have a take-home quiz, you guys can do that. All right. So let's do some graphs, and the graphs I want to do are going to be related to this here scenario. Got a cannon on top of a cliff, just blasting a cannonball. That goes here. Now, remember how we've been breaking down and analyzing these projectile problems. We can either look at what's going on strictly horizontally or strictly vertically. Now, horizontally, the cannonball just moves across the speed or across the field at constant speed. Right? Dx is constant all the way across. It doesn't speed up or slow down, right? Because there's no horizontal gravity. Gravity only pulls vertically, right? We've been ignoring air drag. We're going to continue to do that, right? So it seems to be across. Now, the cannonball does accelerate vertically because gravity pulls vertically. Zoop, zoop, right? But that just, everything feeds into the same kinematic equations we've been using the last few weeks for linear motion. Okay. So let's put it all together and make some graphs for that particular scenario you guys just saw. Here, let me go ahead and write that right here. We got cannon aimed horizontally at edge of cliff. Okay, so that's the setup. That was the picture you just saw. Let me go ahead and define down as the positive vertical direction. Throw in one more thing here. Let me define the top of cliff as 0.0, like 0 meters. Okay. All right. So I got the scenario, and then a couple of definitions just to get us grounded. Okay. Let's do 3 graphs. I'm going to split this paper into 3 parts. I'm going to do 3 graphs. It's not gonna be exactly the same thing. Well, you guys usually, you're used to seeing like graphs coming in like threes, but these can be three different kind of graphs that you normally see. Right, so the way I set this up, these are all going to turn out to be first quadrant graphs. Okay. You guys, in your notes, you make up some XY axes. Okay, so one graph, let's do like the vertical displacement as a function of time. So versus t. Okay. So height in meters versus time in seconds. Okay. Now on that one, remember the fact that I define the top of the cliff as 0.0 and down is the positive direction. Would it be true that at time 0 it's at position 0? So go ahead and put a dot right there, right? Right. At time 0 it's at position 0. Look at the cannonball, right? And then as it starts to fall vertically, it's going to fall in the positive direction. That's why it's a first quadrant graph. It's going to fall positive. Okay. Let me go ahead and set up these next two graphs I'm going to have you guys do. What's the vertical component of velocity as a function of time? That'd be in meters per second. Time is in seconds. And finally, I'll be interested in what's the horizontal component of velocity as a function of time. Be sub x as time is passing along. Tick, tick, tick. Right. You know what, just make it maybe a little bit more concrete. I'll even throw some time values. Let's do 3 seconds. Let's say it's like a 3-second fall. Okay. Okay. All right. So we've got 3 separate graphs, all referring to this scenario, blasting a cannonball horizontally from the edge of a cliff. Okay. We're looking at 3 different aspects. So remember, the first graph is how far did the cannonball fall? Say every passing second. Second graph is how fast is it going strictly vertically, the vertical component of velocity every passing second. And third graph is what is the horizontal component of velocity? How fast is it going across the field every second? Okay. Now, if you guys can draw those graphs before I show you the answers, then that's a really good indication of what's going on in this class. Right? Help you guys out a little bit here. Give you guys 1 point. So at time 0, let's call that position 0. All right, you guys ready to go over the answers? Okay, so start with this one. How far does the ball drop? Now, h could refer to height, but I'm really looking at a height change, like a vertical displacement. Like how far does the ball fall? Okay, so how about this? After 1 second, how far did the ball fall? Do you guys remember an equation goes h equals 1/2 g t squared? You guys know that? Okay, which is true for, let's see, vertical free fall, like how far did it fall as a function of time? It's being accelerated due to gravity. Okay, so let's plug in 1 second. Guess what's 1 squared? 1 times 10 divided by 2 is 5. You guys remember that? You guys remember after 1 second, it'll fall about 5 meters. Put a little point right there. So, okay. How about if you plug in 2? Guess what's 2 squared?
4
Times 5 is 20. So it will have fallen 20 meters after 2 seconds. What if you plug in 3? 3 squared is 9 times 5 is 45. So after the 3rd second, it's fallen a total of 45 meters. Okay. Which, by the way, this picture happens to also align with that, right? 45-meter top cliffs. So you guys see that this example, it would take 3 seconds to hit the ground. Right? Is that the same as what if you took a cannonball and just perched it right on the edge and just gave it a little tap, tap? So it goes just pretty much straight down. Would those cannonballs hit the ground at the same time? Yeah, it takes them both 3 seconds to fall that distance, right? You guys saw Paul Hewitt do the experiment. And what shape is this curve? That's a parabola. Yeah, that is a parabola. Okay. I could have drawn that a little bit better because that's the vertex right there, 0, 0. That's a parabola, isn't it? Right. You guys get that? Right, now let's switch to a different question. Not how far has it fallen, but how fast is it falling? Do you guys remember an equation that goes something like this, GT? Is that? Okay. So after 1 second, how fast is it picked up to vertically? Sorry, let me back up. Even more basic question. Leaving the cannon barrel at time 0, how fast is it moving up or down leaving the cannon barrel? I mean, I say it's not moving up or down at all. So wouldn't that be 0 meters per second vertically at the point of the cannon barrel? So this point does exist on this graph at 0, 0. Okay, because we're looking at vertical. I don't care about the how fast horizontally. I don't care about. All I care about is how fast is it going up and down, and that number is 0 leaving the cannon barrel. Okay. Okay. All right. Now the question that let's get a little bit ahead of myself. How fast is it up to after 1 second? 10 meters per second. How fast another second? Yeah, now we're up to 20. How fast the third second? 30. Because just V equals GT, right? Okay, so every second it's picking up another 10 meters per second, about 10 meters per second squared. Does that graph look like that? Just a straight line? Right. So that's a direct relationship. Linear. Is that okay so far? Right. Now, both of these graphs are, we've just been looking strictly vertical. So in fact, these graphs would be exactly the same for if you just dropped the cannonball or just straight down, right? There's no difference. It's the same thing, right? Here's how far it's fallen. Here's how fast it's picked up to. Right? Now, this last graph, we're interested in a different axis. We're interested in horizontal, like that, right? Let's say my cannonball was blasted like 40 meters per second. 40 meters per second. Right? So at time 0, it's leaving the cannon barrel, moving across at 40 meters per second. So we got that point on the board. Okay. After 1 second of flying across the field, how fast is it still going across the field? 40 meters per second. How about another second? Is it always going 40 meters per second across? Yeah. Yeah. As long as this isn't free fall. There's no horizontal forces, right? Because gravity only pulls vertically, not horizontally. And we've been ignoring air drag. We'll continue to do that. So yeah, it's just 40 meters per second all the way across. Right, you guys got those 3 graphs? Okay. Yeah.
So is there like a formula for one like there was something?
Sure. I guess Vx is just a constant. In this case, for my number example, got 40 meters per second velocity. Okay.
So it's just a straight line.
Yeah, just a flat line. Okay. And if you wanted to really tie it back to these 3 amigos, I would go with the middle one and say there's 0 acceleration horizontally. So this piece goes to 0. And then final velocity is just the initial velocity. Okay. My examples is just 40. Okay. All right. Great. So you guys ready for a Kahoot? Kahoot. All right, let's switch over. All right. Oh, and you guys know that the questions are the same as on your homework page that I'm going to pick up by Monday, right? Okay. So if you guys have that page out, you can follow along. You know what, too? I printed off way too many of these by accident. So if you need a page for whatever reason, extra is right there. Right. All those conceptual questions. Do you guys remember your linear motion take-home quiz? There were lots of conceptual questions straight off that page. I'm about to get you guys tomorrow. I haven't printed these yet, but I've got it made. Projectile motion quiz. I wonder if there's going to be a lot of conceptual questions on that one. All right. Everybody signed on, ready to go. All right, here we go. A vector is a quantity that has both what and what. Yeah, a magnitude and a direction. Okay, so a magnitude is like a number value that you can plug into the calculator. For example, if you say gravity field is 10 meters per second squared down, The number 10 is the magnitude of, meters per second squared, right? And vectors also importantly have a direction. So my example of gravity is 10 meters per second squared downward. Well, downward is a pretty important idea, right? So if you throw a ball upwards versus downwards, well, is the ball speeding up or slowing down? Well, you know gravity's pulling away and you threw it some way, right? So right. Now, if a vector is not, or sorry, if a quantity is not a vector, it could be a scalar, right? For example, mass, which would only have a magnitude, right? But mass has no spatial direction, but vectors do. Is that okay? Right. So if you're adding and subtracting vectors, right? Think about directions, right? Right. James, getting some points. A scalar, for example, mass, is a quantity that has only what? Yeah, a magnitude, right? So I might say mass is equal to 5 kilograms. Right? So 5 kilograms, that can be a magnitude, but that doesn't really have any direction associated with it. Now, if you said weight, if it has a weight of like 50 newtons, right. Well, now that is downward, and now we're back to a vector, right? Is that okay? Right, vector versus scalar, right? Right. So how about if you have different velocities, and you might have like adding and subtracting velocities, those would also be vectors, right? All right, got James, Evan, Cole, David, and Carrie getting points. Suppose a plane can fly 100 kilometers an hour relative to the air, and it also gets a boost from a 60 kilometer an hour tailwind. What's its ground speed? Yeah, 160 kilometers per hour. Yeah, you guys missed it. So let me switch over and draw this one out for you guys. Okay. So we're gonna do we're gonna add some vectors together. That's what we're gonna do. Add some vectors. We get a plane going. Okay. And let's say this plane relative to surrounding air, right? Its jet engines going, right? It's pushing, and it can get up to 100 kilometers per hour. You guys see an arrow there? That arrow, hey, that's a vector. That's a vector. That's a velocity vector, isn't it? Velocity vector. Okay. But what if the whole air mass is also moving in the same direction relative to the ground? That's called wind. Let's say let's go in at like another 60 kilometers per hour. Okay. See how I connected those vectors tip to tail? You guys remember that? Tip to tail vector connection going on right there. Okay. And then if you go from the tail of the first one to the tip of the last one, in this case there's only two vectors. Okay. That will tell you what's called the resultant. You guys remember the resultant? And isn't the resultant that plus that, which is 160 kilometers per hour? Resultant. Right. And that's the plane relative to the ground. So here's the plane relative to the air. Here's the air relative to the ground. Here's the plane relative to the ground. Right? You guys get that? All right. Back over to Kahoot. Oh, cool. We moved to top spot. What is the resultant of a 3-unit and a 4-unit vector at right angles to each other? Ooh. Yeah, 5 units. Now, why is it 5 units? Let me switch over and show you guys some notes here. We can sort of do a plain example again. Okay. We got, suppose I have 4 units that way and 3 units this way. Okay. Now it might be a plane like 4 meters per second and 3 meters per second. If those are velocity vectors, you know what else that could be? That might be force vectors. What if it's like 4 newtons that way and 3 newtons that way? Let me show you guys an example. This guy right here. If I push it 4 newtons that way, it moves that way. if I push it 3 newtons this way, it moves that way, right? What if I do both at the same time? What if I do 4 up and 3 to the right simultaneously? It's gonna move up and to the right. It's gonna move up more than right, because I'm pushing it more that way, right? Oh, do you guys see a tip to tail vector connection right there? Just like before, tip to tail. So if you go from the tail of the first one to the tip of the last one, you get the resultant, which is like the net force on this thing as I'm pushing it around. 4 up, 3 to the right. Okay. So not only will it move in that direction, but you can also use Pythagorean theorem to find the magnitude of the total force. You guys remember Pythagorean theorem? Right, so if I do force total squared equals 4 newtons squared plus 3 newtons squared, right? 16 plus 9. Is that 25? Then square root both sides. F total square root of 25. 3 newtons. 5 newtons. All right. Circle a little bit. Okay. Okay. Guys, hey, guys, that's called a what triangle?
30, 60, 90.
Close, not quite.
And 3, 4, 5.
3, 4, 5, right? No, 30, 60, 90, and a 3, 4, 5 are look pretty similar at a glance, but they have a little bit different geometries. Like a 3, 4, 5, so it calls 5 newtons. Then that's the answer to this one, right? Turns out this is actually not a 30-degree angle exactly, but closer to a 37-degree angle. This one's closer to a 53-degree angle, so pretty close. Okay. Yeah, that is a 3, 4, 5 right triangle right there. All right. So back over to Kahoot. All right, Evan on fire, James at pull, holding on to the leads. A plane flying into a headwind loses ground speed. Plane flying with a tailwind gained ground speed. But what about a 90-degree crosswind? The plane is flying north and it's being blown east at the same time. What is it? What happens to its speed relative to the ground? Ooh, got one winner. Ooh, I wonder who got it. Who got it? Okay. Yeah. All right. Let's switch over and show you guys why. Okay. Actually, you know what? I don't have to write anything new because everything is already written on this paper. So, well, maybe we could swap out newtons with meters per second. So this example on the left is the plane with the tailwind. See how it's going faster relative to the ground? The plane can only fly 100 meters or kilometers per hour relative to surrounding air, but it's getting a boost. Now it's going really fast compared to the ground, right? The shadow across the ground is moving 160 kilometers per hour, right? Now that's all just in one dimension. Now let's take it to 2 dimensions. Instead of newtons, what if it said like kilometers per hour, or meters per second? So the plane could fly like 4 units straight north, and it's in a crosswind blowing east at 3 units. Do you see that its ground speed would be 5 units? It'd still be a 3, 4, 5 right triangle, some version of a right triangle, right? Hypotenuse of right triangle is always along the side. So yeah, so the plane shadow moves like 5 units of speed across the ground, right? Guess that? Yeah, so the plane actually moves faster than it could without the wind, relative to the ground. You got plane relative to the air, air relative to the ground. Put those together, you get the plane relative to the ground. Evan, moving back to the top, on fire. Ball is thrown into the air at some angle. At the top of the ball's path, its velocity is. Entirely horizontal. Now, why would that be the case? Let's go over here and break this one down. All right, so that could be basically this scenario, right? Throw a ball into the air at some angle, goes into that tight path. Right? So I'm gonna take this picture, just copy paste that on a blank page, and then we're gonna analyze this thing. All right, so we got the ground, we got. I think I want to do this. Let me just give it a pretty steep angle. Alright, got ourselves a ball. That's the throwing speed, right? Okay, you see it's gonna go. That gravel path right there, right? Suppose this whole process takes 6 seconds. So we got 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, right? Tick, 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 tick. Okay. Do you guys see the ball like slowing down on the way up? A little slower, a little slower, a little slower. And then it's like speeding up on the way down. A little faster, a little faster, a little faster. Okay. And slower and faster, look, those like magnitudes of velocity. And I'm representing that with the vector arrows are getting a little shorter on the way up. And they're getting a little longer on the way down. Right, you get that? And the question that the target question you guys just answered is at the very top, its velocity is entirely what? Horizontal. You guys see horizontal? Right. Okay, let me go one layer deeper of analysis. And can I break these velocity vectors into components? So like this much to the side, this much up, this guy, this much to the side, this much up, this much horizontal, this much vertical, and then, well, there you go. Trying to do this somewhat accurately. Picture might not be exactly in scale, but pretty close enough to make the point. Trying to make here. Right. See, I just took each of those velocity vectors and broke them into blue components. Is that right? Now let's look at the vertical component. Suppose this is like 30 meters per second vertical. How fast after 1 second vertical? 20, then 10, then 0, and then it goes down 10, down 20, down 30, right? That's in the vertical direction. What about horizontal? Suppose it's going like to 12 meters per second to the right. Is it 12 there, 12 there, 12 there, 12, 12, 12? You guys see that horizontally it stays exactly what it's doing all the way across, right? And at the top, it's entirely horizontal, right? You guys remember that? Back to Kahoot. All right, got Evan, James, Cole, Capri, Catherine, top 5. A ball is thrown into the air at some angle. In the first second, it moves 5 meters horizontally. How far horizontally in the next second? Yeah, also 5 meters. I just showed you that on that page, right? Where, here, flip my screen over real fast. Do a quick one here. Remember how the horizontal component of velocity stays the same? So suppose that value was like 5 meters per second. So during the first second, it would have moved 5 meters horizontally, but that'll stay constant throughout. So every second it's moving another 5 meters, right? Back over here. Evan on fire, still top spot. Projectile maintains its horizontal component of speed because it's not acted on by any what? Yeah, horizontal forces, right? So vertically, it's changing its velocity by 10 meters per second per passing second because gravity pulls vertically. But horizontally, gravity doesn't pull horizontally, so there's no gravity force, right? And we've been ignoring air drag, and we're going to continue to do that. So yeah, so there's no horizontal force. That's why it just constant velocity all the way across. By the way, that's also related to Newton's first law of motion, which we haven't quite got to yet, but that's a good example of that. Newton's first law of motion, called law of inertia. Okay, if there's no force on something, it's just going to keep doing whatever it's doing. In this case, constant horizontal velocity. Number 9, at what part of a path does a projectile have minimum speed? Yeah, top of its path. So one perspective on that is, you guys remember back to linear motion? You guys saw this in linear motion. If you take a ball and throw it straight up, that's the type of projectile, right? And then at the top of its path doesn't have 0 speed, which would be minimal for that case, right? And then if you take that to 2 dimensions, flip over here, you guys see how it's like slowing down on the way up and then speeding up on the way down? And then it would have minimum speed right at the top. Got Laura on fire, James and Evan, second and first. If a cannon fires a cannonball horizontally off a cliff at 30 meters per second, how far horizontally will the cannonball move in 1 second? Yeah, 30 meters. Because if it's going across the field at 30 meters per second, then every second it goes across at 30 meters. Right? Notice this question has nothing to do with the vertical direction. Right? I mean, as long as the cliff is tall enough, it can still be a projectile. Right? That's all I care about. Right? It's only asking about how far across the field. That's a horizontal question. X equals VT. Ooh, here at part 2, on fire, moving up. Okay. All right, Evan's still in the lead. It is easier to hit a home run in Denver, Colorado than in Miami, Florida. Why would that be? Ah, you guys got it. Yeah. All right. So I know you just said a couple minutes back we normally ignore air drag in this class, but there's a couple questions here and there where you might think about, okay, say if you're comparing something, and this is one of those cases where it might make a difference. So you guys know down here at sea level in Florida, well, we have like maximum air pressure, right? one atmosphere. Right? How many of you guys ever gone up to say like Denver or up in the mountains like a mile high? Yeah, some of you guys. Right? And you guys ever try to like running around? Normally you lose your breath pretty fast. In fact, a lot of athletes like to practice up in the mountains because it's really hard, right? It's really, and they come back to sea level and their body thinks, oh, there's so much oxygen down here, right? Yeah, so the atmosphere is really thin. Yeah, so this is an air drag question. So not very much air drag up a mile high. It's true too, up in that stadium, a lot more home runs. Cheeser. In the absence of air resistance, the optimal angle to throw a ball the furthest distance. It is a 45-degree angle, 45 degrees. Let me do something a little bit off the beaten path here. So let me show you guys the math proof behind this. Right. So here's the premise. You're with your friends and you're in a baseball throwing contest, and the question is who can throw the baseball the furthest, right? How can you maximize this X? Well, you can't really affect your maximum throwing speed. You can throw however fast you can throw, but you can affect this angle. Do you guys think if you throw it at a shallow angle, it's gonna go just land pretty much immediately? You guys think if you turn this up to 90 degrees, it's gonna just land on your head? Right. So also not go very far. But there's some angle where it will maximize this X, right? Where, okay, you guys get that premise? All right, so what could that be? I'll show you guys the proof. So would be that X equals the horizontal component of velocity times time. Horizontal component of velocity, isn't that V times cosine theta, right? Then what you do is you take the time. Now the time is in the air. Would that also be related to the theta, right? Because shallow angles, not very much time. Steeper angles, it's gonna be the air for longer, right? So you need to get time in terms of the angle, which you can do this way. This is one way to do it, not the only way. Okay. Substitute that in, x equals vt. Here's your horizontal velocity, here's the time expression. Okay. You guys might remember a double angle identity from a trig class. You can get the range formula. So now with this range formula, you can figure out how far as a function of the theta. Right? These values are constants. Okay. Now, if you want to maximize x with an optimal angle, that turns into a calculus question where you say, well, the rate change of how far is a function of angle, that would have to zero out. So if I throw it 0 degrees, it's going to not go far. Right? If I throw it at 9 degrees, it's going to come back and go also 0. Right? But what's the angle I can pitch it at to go the furthest distance? Well, the rate change of that curve would be 0. Right? So you need a rate change equation, which you get from calculus. It's like this. Set that equal to 0. Get cosine of the double angle is equal to 0. Therefore, the double angle itself must be 90 degrees because that's where cosine is 0. So you can solve for the angle 45 degrees. Right. So that's way beyond the scope of this class. So, but just wanted you guys to show you guys that's there. That's how that would be done. So you're like, oh, okay, yeah, I can kind of see that. Just big picture idea, right? Yeah, 45 degrees, 45-degree angle. I will maximize the range. All right, got Capri in the top 5, Carrot Part 2, Bora on fire, James and Evan in the lead. Cannonball launched 30 meters per second over flat terrain in the absence of air resistance. It will land at a speed of. Yeah, also 30 meters per second. So it's it slows down on the way up and then speeds up on the way down. But this could be a symmetry question, right? So at every elevation, it has equal speed, as long as you ignore air drag, which we do. Okay, so there you go. Slow it down on the way up, speeds up on the way down. Is there any question why that would be? You know what, let me show you guys real fast. Show you guys something here. Flip over. Suppose this was 30 meters per second. And then maybe it's like 25, 20, 15. And then it goes 20, 25, 30. Right? You guys do that? Okay, those numbers wouldn't work out exactly like that, but that's sort of the idea, right? Projectile launched horizontally, hits the ground in 1 second. If it had been launched at a faster speed, what would happen to the fall time? I got one winner. One winner. Stay the same. Let me show you guys why it would be the same. You guys remember that Paul Hewitt demo where he had that device rigged up with the 2 marbles, right? And then he blasted one to the side and let the other fall straight down. And which one hit the ground first, or did they hit the ground at the same time? Same time. So that actually is this question, isn't it? Because if you drop a marble, it takes some time to hit the ground. If you blast one to the side, it takes the same time to fall the same distance vertically, right? Right. As long as you blast it horizontally. Okay. So it doesn't matter how fast you blast aside. Well, actually, that's not exactly true. As long as you're not overcoming the curvature of the Earth, which we've kind of been ignoring. Okay. Yeah, there you go. Okay. If you assume a flat terrain. Object thrown horizontally at 30 meters per second. What is the acceleration in free fall? Acceleration. Yeah, anything in free fall at the surface of Earth, it's always 10 meters per second squared downward, right? It doesn't matter how fast it's moving, which direction it's moving, right? Gravity always pulls 10 meters per second squared downward. Is that okay? Right. And that's strictly vertical. All right, Evan, still on the lead. Neglecting air drag, which we always do. At what point is acceleration greatest for a ball thrown straight up vertically? Yeah, it's the same everywhere. In fact, you guys can attach a number to that. What is the number everywhere? 10 meters per second squared downward, right? Doesn't matter how fast it's going, what angle it's going. Right? It's always accelerating down at 10 meters per second squared, as long as it's in free fall. Right? Free fall meaning there's only one force acting on it, its own weight. Okay? Accelerates down 10 meters per second squared. Suppose you can jump 1 meter vertically. If you were on a skateboard moving 15 meters per second to the right, then you could jump how? Does your horizontal motion affect your vertical motion? Nope, same height. It's the same height. So we're gonna move on a little faster. More on fire. Evan's still in the lead. 3 questions left. In orbit, a satellite is this one we're looking for is just a projectile following around the curvature of the planet. Turns out if you go 8,000 meters per second to the like horizontally, then by the time you fall 5 meters in 1 second, that also matches the curvature of the Earth, right? So you are accelerating. It's a special kind of acceleration called centripetal acceleration, kind of a future topic, but yeah, kind of a expanded scenario there. Ball thrown straight up at 20 meters per second will return to the ground with the speed of 20, 10, 0, 10, 20. Did you guys say 20 meters per second? Oh, yeah, you did, because, all right, it's symmetry, right? Cannon, barrel velocity, 120 meters per second, launches the ball off a cliff. How far will the ball fall in 3 seconds? Go to the edge of the cliff and drop a ball. How far does it fall in 3 seconds? 1/2 GT squared. Is it 45 meters? 45 meters? Doesn't that have nothing to do with how fast it's going horizontally? You guys said 45 meters, right? All right. Let's look at the winner podium. With the bronze, James. With the silver, Mora. And the gold goes to Evan. Oh, yeah. Kahoot party. Got Carrot Part 2 and Cold. All right, you guys have a great rest of your day. I'll see you Friday.